Okay, welcome back. If I'm not mistaken, last time we stopped right before introducing vector spaces. I'm right. We have been talking about the cross product and the dot product and the geometrical meaning of them and why they are important in computer graphics and how we are going to use them. Now we have to brush up a little bit vector spaces and matrices. I will be rather quick because I gather that you know already more or less this material. Every set of vectors that we use in computer graphics belong to a vector space. We have to ensure this because the vectors belonging to a vector space is a warrant for us that we can apply a set of calculations and simplifications and methods that guarantee a good result when we are creating bounding volumes for general shaped meshes and when we are checking visibility determination between any given mesh and any viewing volume. What is a vector space? Is a set of vectors. Well, of course, if we are considering 3D spaces, then it's a set of 3 vectors. But if you want to do, I don't know, anything more conceptual, you can go to 4D or 5D. There is no limitation about this concept. So it's a set of n vectors for an n-dimensional vector space, which has the following properties. S is a closed set under addition. It means that if you take a vector that belongs to a vector space and you sum to another vector that belongs to the same vector space, the result is yet another vector which belongs to the same vector space. That means being closed in relation to a specific operation. S is a closed set under scalar multiplication. That is, you multiply a scalar by a vector, you still get a vector belonging to the same vector space. There exists only one element in the vector space called the null element, such that you add it to the vector in that vector space and you keep getting that vector, so the neutral element under the addition. For every element P in S, there exists an element Q in S such that P plus Q equals to 0. That's the inverse element. Addition is associative, scalar multiplication is associative. So here, as you can see, the set is of n vectors, so V1, V2, V on n. And the other very important property is that this set has to be, the vectors belonging to the set, have to be linearly independent. That is, it does not exist any real number, a1, a2, an, where at least one of these not 0, such that you combine them and you get 0. If there is such a combination, on the contrary, then the vectors are not linearly independent, but they are linearly dependent. If you have a vector space with all the properties I have already told you, and the set of these vectors are linearly independent, then you have what we call a basis, a vector basis. Just to give you an example, any set of coordinates that we use is a vector basis. If you want to use in 3D, well, Euclidean geometry, in 3D a set of vectors to base your coordinates on, and we have seen what was the meaning of this last time, when we have seen that we have one vector which is every vector that we specify with a set of coordinates is actually referring to another set of vectors which is the reference system. That is the set, the basis, the vector basis that describe the coordinates for each vector that we are manipulating. We have seen it. Hello, hello, please take a seat. So, you want to make your own coordinate system, you're welcome to do so. Just you have to take care that the vectors which are forming your coordinate system are a basis, meaning they form a vector space and they are linearly independent. Plus, you can have a vector space, where a basis, and you can require that this basis is orthogonal. This is actually not necessary if you want to complicate your life. You could take for yourself a blonde, beautiful girlfriend, plus using a non-orthogonal vector space. But if you want to make life simpler, you could choose to live alone and choose a vector basis which is not only a basis, but in which the elements are orthogonal. Right? What does it mean orthogonal? That if you take the mutual dot products between all the possible combinations, so Vi, dot product, Vj, take all the permutations you need, you always obtain 0. That is orthogonality condition. This is the famous or infamous XYZ orthogonal basis that we used since our childhood. Plus, again, you can put yet another condition which is useful to do something that I'm going to tell you later, not only orthogonal but also orthonormal. If you require the basis to be orthonormal, it means that for every pair of elements ij, you have the orthogonal condition. That's okay because you require your elements to be orthogonal, plus each scalar product equals to 1. It means that you're using normal vectors, vectors with norm 1 as the basis of your system. So, an orthonormal basis, that is a vector space which is orthogonal with orthonormal property, is, for example, this one, x, 1, 0, 0, y, 0, 1, 0, z, 0, 0, 1. These are the three x, 1, z in their orthonormal form. This is usually what you use to specify coordinates. Orthonormal basis is what we will always use to specify object coordinates in computer graphics. Why? Because if we are working under an orthonormal basis, we can safely apply transformations without changing the elements. So we can move a vector, for example, without changing its length, just because I am putting a moving operation on it. So I have a vector, well, like this. I want to move it in space. I don't want it to I don't want that it gets bigger or shorter just because I moved it. Okay? I want just to move it, not to change its length. How can I be sure of that? Well, if I'm working in an orthonormal basis, then I can apply, for example, translations matrices to translate the vector with guarantee that I am not making any other change to that specific vector. There are, of course, more subtle changes, like, for example, when you're moving entire shapes, for example, triangles, or even segments. It's very dangerous, for example, if you calculate the normal to a vector, and then you move that vector, and if that transformation is not under an orthonormal basis and not made with an orthogonal transformation, we will see it in a few seconds, then you do not have, for example, guarantee that your normal stays correct. So you move it, and if you use the same normal, that same normal that you calculate before the transformation is not valid anymore. You have to recalculate. So, to preserve some topologic characteristics, I've written here in nice words, you have to use orthogonal matrices in n orthonormal vector sets. So this set, it's the time to introduce matrices. Well, I'm sure that you know them already. As you know, the matrix M is an n by m mathematical object. It's an array of numbers. So n rows and m columns. If n equals to m, the matrix is called square. You can multiply together two matrices, provided that the number of columns in A is equal to the number of rows in B. Then you might remember that you can transpose matrix just as you transpose vectors, but the rule is a little bit different, because with the matrix, of course, you don't have just a single column of numbers, so you have to exchange the entries ji, ij, transpose the matrix. You can multiply matrices by a scalar. You can multiply together two matrices, but the number of columns of the first matrix has to be equal to the number of rows of the second matrix. It's the famous multiplication rows by columns. The sum of matrices is commutative. However, and this is extremely important in our case, multiplication between matrices is not commutative. This, of course, descends immediately by the fact that I have been telling you that you can multiply matrices only if the first matrix has a number of rows, has a number of columns equal to the number of rows of the second matrix. This implies that you might be allowed to make the multiplication in one direction, but if you change the order of the matrices, that multiplication might not be possible, feasible. So multiplication is not commutative. This has a strong impact on computer graphics, because we represent transformations, that is moving around objects, scaling objects, rotating objects, by multiplying a special matrix, which is called a transformation matrix, to the vector, which is representing either the point coordinate or the direction. You can compose more than one transformation in one go by taking transformation matrix, for example, for rotation, number 1, then you can apply a translation, then you can apply to the vector. So you would say, I multiply by the rotation matrix, then I multiply by the transformation matrix, then I multiply by the vector. In this way, you create a roto-translation of that specific vector. If you invert the order of the transformation matrices that you apply, you get a different result. We will see it. Then you have something which is called the identity matrix. It's a square matrix which has zeros everywhere, except on the diagonal, which is composed by ones. Then there is the concept of an invertible matrix. You can invert only square matrices, and the property of the inverse matrix is that if you multiply by the matrix which is originating from, then you get the identity matrix. Not every matrix has an inverse. If the matrix has not an inverse, that's called a singular matrix. An example of a singular matrix is a matrix with a row, one row, or one column, all made by 0. Or a matrix with 2 rows with the same numbers, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. Why? Because that depends also on the determinant, right? Do you remember? Well, let's introduce the determinant. But a matrix is invertible if and only if its rows and columns form a set of linearly independent vectors. This is related to the determinant. What's the determinant? The determinant of a square matrix is a scalar quantity which depends on the elements contained in the matrix. I indicate the determinant with the delta symbol, the capital delta. That's the determinant of the matrix M. Do you remember how to calculate the determinant of a 3 by 3 matrix? You alternate sign. Do you remember the pseudo-determinant ijk? We did it last time. So basically, you calculate it by multiplying the elements of the first row with alternating signs by the determinant of the submatrix 2 by 2 that you obtain by taking away the row and the column of the element on the first row we are taking as a reference. You should remember these, right? Some important properties. If you exchange two rows in a matrix, you negate the determinant. That is, if the determinant was 3 of a specific matrix, you exchange the order, for example, of two rows. The first row you put it as the second row. The second row you put it as the first row. You obtain the same determinant in absolute value but with an opposite sign. If you multiply a row by a scalar A, it's like multiplying the determinant by A. If you add a multiple of one row to another row, you do not change the determinant. The determinant of a matrix with two identical rows is 0. These rules are useful when you want to find the solution of a linear system. You remember? You have a linear system which represent, well, a set of equations. You want to find the solutions. Everything actually in the end comes to creating this matrix of coefficients and the matrix of the equations themselves, and you have to manipulate it until you get something like this. I have it around here. Until you get something like this that gives you the solution in which you can put x and y and have the solution to your linear system. In order to manipulate the matrix, what you do, you multiply one row, you sum to the other row, you subtract the twos, okay, until you get 0 in the end and the solution in the first row. You remember? I think in high school, that's the exercise that you do in high school. For those of you who are interested, this is the general formula to calculate the inverse matrix if you know the determinant. It's just for your reference. You don't have to know it by heart, of course. But just in case you need it, it's there. And this is the general formula for any matrix with any number of elements. And finally, we come to a couple of our friends that you might remember. That's the eigenvalues and the eigenvectors. Do you know what eigenvalues and eigenvectors are? Do you know Italian? Right. The eigenvalues is autovalori and the eigenvectors is autovettori, of course. Let's go to the definition. If you have an invertible square matrix, there exist vectors that, when multiplied by the matrix, are changed only in magnitude and not in direction. As you can understand, this already sound like very interesting. It's very interesting properties for us practitioners in computer graphics, because we have a guarantee that if we use these vectors for multiplication, then we have guarantee that we do not change directions of the elements to which we apply them. So if I want to change something on a vector, I have a guarantee that I'm not changing its direction if I'm using a specific vector with specific characteristics which are related to eigenvalues and eigenvectors. Hello. If you want to put into a formula this definition, you take a matrix M, then you have some vectors, V with I. If your matrix is 2 by 2, then you have two vectors. If your matrix is 3 by 3, then you have 3 vectors, and so on. And if you use an eigenvector and you multiply that matrix by that eigenvector, what you get? The eigenvector again, possibly scaled, but not change in direction. Do you see? It's here. It's here. This lambda value here is called the eigenvalue. This vector v over here is called the eigenvector. So, given this relation, how you can determine which are the eigenvalues and which are the eigenvectors? You just rearrange the equation. You take your matrix, you take this term over here, you put it on the other side, and you have the equation. This is the infamous equation for eigenvalues and eigenvectors that I'm sure you know. But of course, if you want this to have a non-trivial solution, what is the trivial solution? It's written over here. Well, it's simple. I put an eigenvector 0, that's my eigenvector. But then my definition of a vector which multiplied by the matrix does not change in direction, okay, has no sense anymore, because this vector is 0, 0, 0, right? So we have to guarantee for all this thing to have sense that there is no trivial solution. In order to avoid that the trivial solution is possible, we need to ask that the matrix M minus the eigenvalue multiplied by the identity must be singular. Singular means with what's a singular matrix? Didn't I say it? The determinant is 0. In this way, it is not invertible. If it is not possible to invert it and multiply to the right, you can't have the trivial solution. So that's the trick. How do you apply the singularity request? Well, you search the values of the eigenvalues of lambda that make determinant equal to 0. And this is one of your worst enemy, which is the characteristic polynomial. Do you remember that day in September? The roots of the characteristic polynomial are the eigenvalues for the matrix M. Once you determine the eigenvalues, you can calculate the corresponding eigenvectors. One eigenvector for each eigenvalue that you calculated. So it depends from the roots of the characteristic polynomial. Since the matrix is singular, it has at least one row of zeros when you solve it in the system. So you have infinitely many solutions. So every eigenvector that you get as a solution to this equation is always expressed in terms of its eigenvalues. You can choose the arbitrary constant related to each eigenvalue in the eigenvector in a way that the eigenvector has unit length. Okay, that's very practical. I think I have an example. I think it's here. Right. Why do we care for eigenvectors? Well, why do we care for eigenvalues? Because we need eigenvalues to find the eigenvectors. Right. And why do we care about eigenvectors? Because if you create a matrix made with eigenvectors, you have the guarantee that that matrix is orthogonal. And why do we like orthogonal matrices? Because, as I said, if we use orthogonal matrices for transformation, they keep dimensions, angles, as general structure of any point or shape that we transform during rotations, reflections, translations. Another fine use, another cool use of eigenvectors is that eigenvectors form an orthogonal basis. Not really orthonormal, it depends. It could be orthonormal if you have care to choose the scaling constant in a way that every eigenvector has a norm equal to 1. Then you would have a set of vectors which is not only orthogonal but also orthonormal. But in general, eigenvectors give you immediately, free for use, a set of vectors which is orthogonal. In this way, you can use the set of vectors as a coordinate system. This technique, for example, is used to calculate the natural coordinate system, which is also called the natural axis, for any specific volume. What is the problem of the natural axis? I will draw for you briefly the problem. I will bring it again to your attention later on when we will be doing Bowden volume calculation. That's supposed to be this, I guess, and this. Why do we care about finding axes or finding a different set of axes? Like, this is our nice set of axes, right? No, let's make it bigger. We can say x, y, z. As an orthonormal basis, it will be like this. In this orthonormal basis, we can specify coordinates, coordinates of points. Every one of these points is a vector itself. So you could say that this is, I don't know, I'm just shooting in the dark, right? 3 numbers, it's a vector. But it's not a vector representing the coordinate system. It's a vector expressed over this coordinate system, right? You have many of these vectors which represent which gives me a question. I say this is representing this specific point, but these are representing the axis. Don't you feel it's confusing? What do I have? Do I have a system to avoid confusion between this, that is a point in the coordinate system, and this, which is the coordinate system vectors, directions? Is there a system to avoid this confusion? Yes, right. We use homogeneous coordinates, which is fourth coordinate here is why it's 1, and here it's 0. How do you remember that? You should remember it without any doubt. Why? Because if you have P1 and P2, do you remember I drawn to you this example? So this is supposed to be x, y, z, 1, right? x1, x1. This is supposed to be, shoot, so x2, x1, y1, z1, 1, okay? It has to be 1, because when you make the vector P2 minus P1, which is Q, which is a direction, okay? Then you subtract every coordinate, and here you subtract the fourth coordinate, and you get 0. And it's correct, because it's a direction, you see? You can't go wrong. When you are in doubt, is it 1 or is it 0? You can't go wrong. Because the direction is always a subtraction of points. So it has to be 0 for the direction and 1 for the points. Right, what I was saying. Okay, I have many points. These points form a mesh. I don't know, it's a kind of fish, a computer graphics fish, which I'm drawing in real time with triangles. Okay, you can see it's a fish, right? Genetically modified fish. Okay. As you can see, these coordinates are quite complex, and working in this set of coordinates is complex, but moreover, if I'm using these axes to create a bounding volume around the mesh, I can say, the idea is I put the mesh inside the volume. Okay? Why? Because when I want to check if the fish is going outside a certain area, or if another fish has collided with the first fish, okay, this is the other fish. What do I do? Of course, I do not check every single point of the mesh. What do I do? I check the collision between the mutual bounding boxes. Do you see? I'm not checking everything. I just check the boxes in which the objects are inside. What's wrong with this approach? But for example, in this case, I get a collision here. But do you have a real collision? No, because actually the bottom of my fish is here, so there is a lot of distance yet. This leads me to the problem. Okay, the bounding box approach is interesting. The approach means the approach means this, that my idea is to put every mesh inside the box and to perform checks on boxes and not on the meshes themselves, because checking on the boxes is far more efficient. However, it can be very inaccurate. When it is inaccurate? When, for example, the mesh has a privileged direction. It has a natural axis in which the points are distributed. Like, for example, here, you see, a fish is a long fish, and it has a natural direction, like this. When it has such a marked natural direction, a bounding box approach, which is using the world coordinates, these are the world coordinates, I mean the coordinates of the whole scene, generally is not the best approach. What you would like to do is to find the best fitting bounding box, which is always the one which has one axis aligned to the natural axis of the mesh, and the other axis arranged as an orthonormal or an orthogonal basis, like this. So instead of choosing x, y, z, you could choose another set, u, v, and w, and create a bounding box using the u, v, w axis. But in order to do this, you have to be sure that you are using an orthogonal basis. It turns out that the eigenvectors of the correlation matrix of the mesh are such axes. So the eigenvectors of a correlation matrix of the mesh, I'm going to explain this, are the optimal axes in order to align it. And why the eigenvectors? Because we have to be sure that they are orthogonal and that they are a vector space. They form a vector space, which is something that eigenvectors always do. So this is one of the application, one of many applications of these things. What is a correlation matrix? I will show it to you later. It's a matrix made with values in which here at the corners you put a value of, how to say, well, correlation, likeliness between points. For example, you see that you have a very high correlation here between x and y. We could say that almost x is proportional to y by 1, because it's, you see, almost on the x equals to y line. So that would show in the correlation, if I'm not mistaken, over here, you would have something like this, very near to 1. That would mean that you have this kind of correlation. And then you have values which are more or less different according to how much they are sparse around in several directions. The correlation matrix is a concept that I will define later that is taken from statistics. Did you ever heard about it on statistics? Correlation matrix? When you want to study how data are distributed, then you usually study the correlation matrix of the data that you are gathered. That's the same thing. This was just to assure you that we are not talking about eigenvectors, eigenvalues for sport. We are doing it because it's useful to solve complex problems in computer graphics. Look, this is an example, if you just want to briefly brush it up because you forgot, of how you calculate eigenvalues and eigenvectors. This is the matrix. You take this matrix. You want to calculate the eigenvectors of this matrix. Then you have to do this matrix over here, and then you have to calculate the determinant of this matrix, which gives you the characteristic polynomial, which is this one. It's half here and half there. You see? This has roots. How many roots? In this case, 2. Lambda 1 and lambda 2. These are the eigenvalues. Then you take the bigger eigenvalue and you label it 1. Then you order the eigenvalues from the higher to the lowest, and you number them. So the higher is 1. The next second higher is 2. The third higher is 3. And so on. Well, not higher but less high. So lambda 1 is 2 and lambda 2 is minus 2. We only have 2 in this case. So when you want to get the eigenvector, you say, I want to calculate eigenvector number 1. So I take eigenvalue number 1 and I put it into the matrix over here. And I try to solve the linear system, this linear system. Don't I have something more? Oh, here. The linear system made by this matrix plus x, y, over here, that's the eigenvector, and 0, 0. How do you solve it? Well, this is the result, minus 1, 1, 3, minus 3. Before start manipulating it, you always have to take care that you have in the top left corner 1. So here I multiply everything by minus 1, so this doesn't change anything. 1 minus 1, 3 minus 3. And then I multiply by minus 3, and I add it to the second row. So the second row goes to 0. And that's the result, basically. So the result of this one is x minus y equals to 0. So it's actually here. V1 is A1, 1, because x equals to y. So x, 1, y, 1. So you can take any 1, 1, any vector, 1, 1, 2, 2, 3, 3, 4, 4, because the result is x equals to y. X minus y equals to 0. If you want to take it normal, then you could normalize it. And if you normalize all the eigenvectors that you get, then you get a basis which is not only orthogonal but also normal. This is the first eigenvector. If you want to do with the second eigenvector, you do the same thing, but here, instead of plugging in 2, you plug in minus 2. You remake the calculation, and you get that the second eigenvector is 1 minus 3. Do you remember these things in your nightmares? Okay. We will use them shortly. But during the exam, actually, you don't really need to know how to calculate eigenvalues and eigenvectors. If you hopefully have a scientific calculator that does vector calculus and matrix multiplication and all this stuff, you can do it with your calculator. Okay, so this concludes the brush up with matrices and linear systems. That was for the series something you should already know, but I am not sure you know. And let's start with something that you might know, but probably you don't, which is how we represent lines in space. A very convenient way to represent lines in space is representing them with a parametric lines. Do you remember this? Probably not. So you take 2 points, P and Q. Any 2 points in 3D, you can define the line crossing these 2 points in 3D parametrically, using a parameter, for example, T, like this. 1 minus t multiplied by p plus t multiplied by q. It works because when you are in p, t equals to 0. So this goes to 0 and this goes to 1. And it gives you that p equals to p. That's correct. If you are in q, t equals to 1, which means that p goes to 0 and p equals to q. So you have basically a parameter which is ranging from 0 here to 1 over here, with all the values in between, which you can use to represent a specific point over this segment. You can even use values of the parameter which is negative, so then you are referring to points which are before p, and values of the parameter which are greater than 1, which means points on the line after q. If you limit this parameter and you say, I forbid the value of this parameter to be less than 0, so you pose a limitation that t is always equal or greater than 0, we have what we call a ray. A ray is a line with a single endpoint, like this. As you might understand, this kind of representation of the ray is important in a specific rendering technique which is called ray tracing. Perfect. So when we will be dealing with ray tracing, we will be calculating rays. What are rays? We represent them mathematically like this. If you have a ray representation, then you could write it in a slightly different way, which is using the origin of the ray plus its direction as a vector. It's easy to go from the segment representation over here to the ray representation over here, because V as a direction can be calculated very easily. How? Making Q minus P, or P minus Q. It depends which direction you want to go. So, you can do it like this. P on the parameter T is its origin plus the parameter multiplied by the direction of the ray. Now that you have a ray in your pocket, you can start using it for a few everyday calculation, which is, for example, determining the distance between a point and a line. So here, you have a line represented as a ray. Where's my pointer? Over here. So this is the ray originating in P with direction V. You have a point Q. Question: what is the distance of this point Q from the ray? You can have, what is the distance of the point Q from the ray? What you do, you find the vector Q minus P. You project it on V and calculate its norm. You know how to do this because you remember that we reviewed parallel components and perpendicular components. So what you're doing actually here, you're making a parallel component of P over V, of Q minus P over V, and you take its norm. Then this means that you take this part here. At this point, you have this vector of which you can find the norm. You have this vector, which is the parallel projection of Q minus P over V, of which you can take the norm, and then use the Pythagorean theorem, using Q minus P as a norm, as hypotenuse, and as a cathetus, the norm of the parallel projection. And then you get the distance. That's a way. Very geometrical. This is the pencil, and this is an exercise for you. To check if you have understood these concepts, consider this small problem and try in the intimacy of your room where nobody is looking at you and nobody can realize how rusty you are with calculations. So you do it without nobody realizing that you suck at these things, but you do it, and try with a point, a ray with that origin, that direction. You consider another point, calculate the distance. Okay? See if you can do it. If you can't do it, don't panic. Take a shower. Go back to your desk. Do it. Because if you're stuck here, then you will be so much stuck later. So unstuck yourself as soon as possible with the exercises. Then, now a very, very useful thing. For those of you, are there any of you who are also doing sound engineering or sound something? Sound, the course of sound engineering? Okay. Most of these things, you know, well, we are describing objects in space. And we are describing distances, how these objects move in space. And this is not useful only for computer graphics, you know. It's useful for robotics. It's useful for modeling how sound sources move or interact. So you study this here, but either you've already studied for robotics or any kind of sound processing course, or you study it now and you will find it useful also in the future for other courses. But one thing which is particularly useful, that I use again and again in very different contexts, is representing planes as vectors. Did you ever hear that, about representing planes with a vector? Does anybody of you know that? Well, how can you represent a plane with a vector? I will explain it to you. Let's start from the definition. you take a point in 3D space which is called P0. And you take a vector n which is normal to the plane and passing through the point P0. And of course, this normal, it's a normal, it should be perpendicular to the plane. Therefore, the plane can be defined as the set of points, well, all the points in the plane P for which this relationship holds true. That is the scalar product between n and any vector which is obtained by P0, the point of origin, and any other point P belonging to the plane equals to 0. So you take a P. P0 you have. It's from the definition of the plane. N you have. It's given to you to define the plane. Then you want to know, does the point P belong to the plane? If the point P you are checking minus P0, scalar the normal, equals to 0, then yes, that point belongs to the plane. You see why? Because if this is P and this is P0, then this is P minus P0. Scalar by n, it should be 0 because it has to be orthogonal. Every point, every vector constructed this way has to be orthogonal to the normal. Right? Did you understand? Yes. Fine. Now, but we also know the Cartesian equation of the plane. You remember it? Ax plus by plus cz plus d equals to 0. That's the general form of the plane. It turns out that A, B, and C are actual, they do actually form the vector n. So the normal to the plane, what are the components of the normal to the plane? Actually the coefficients of x, y, z in the Cartesian form. How can you be sure of that? Well, you just equate the two definitions. Because ax plus by plus cz plus d equals to 0. That's the Cartesian definition. And that's the vectorial definition. N scalar P minus P0. So, you equate them. If you equate them, you can see that ax plus by plus cz is actually n scalar P. Why? Because P, being the general point, is x, y, z. Right? So it is actually true that n is a, b, c. Therefore, d equals to minus n scalar P0, which is the remaining part of the equation. From all this derives this thing. It's very easy. If you take any point Q, its distance, therefore, from the plane is n scalar Q plus d, which is the remaining part of the equation. So, if it belongs to the plane, it goes to 0, as we said, because it's on the definition. If the result of the scalar plus d is different from 0, then you have an information which is the distance. You have an information. One, that that point is not belonging to the plane. B, you have a scalar which tells you the distance of that point from the plane. C, you can see the sign to check on which side of the plane the point is. If D over here is positive, then the point lies on the positive side of the plane. If D is negative, then the point is in the negative side of the plane. What is the positive side of the plane? The one we said it last time when we were talking about, you remember, front culling, back culling. What is the front side of the polygon and what is the back side of the polygon? How do you tell it? The right-hand rule, I use it when I'm making what? When I am making a cross product and I have to determine which is the direction of the result. So I use the right-hand rule, that's right. But I have a definition. The outgoing direction of the normal defines the front side of the polygon. And in this case, define the positive side, the front side of the plane. So this part over here, this part pointer. So this part over here is the positive side, and this part over here is the negative side. You see? Because the vector, the normal, is outgoing in this direction, so over here it's the positive side, under here it's the negative side. So when I'm doing that calculation, that is, I'm calculating the scalar between Q and the normal, plus, if there is one, a D, because that's the coefficient of distance between the origin. If that's positive, then it means that it lies on the positive side. Look, let's see if I can make a drawing. I mean, this is the origin, right? This is D, right? If Q is over here, then this distance is, sorry, I'm drawing with the touchpad, it's not exactly, Q, scalar N, plus E, and that's your distance over here. Like that's the P. And this is a vector, and this is a vector. So, this, for example, this test is very easy. It's just the normal to the plane plus the point. You can determine very quickly if a vertex of a mesh is inside or outside the planes of a viewing volume. That's very easy. If you think about a viewing volume, you can think about a viewing volume, well, as a frustum. Frustum is a piece of pyramid. As you can see, you have planes, 1, 2, 6 planes. Each one of these planes has its equation. So it has its normal. Normal 1, normal 2, they are actually arranged like this. All the normals in the viewing frustum are arranged inwards, so they are all positive inwards. So when you're taking a general point Q of a mesh, so this is the mesh, this is one point. You want to know, is this point inside or outside the viewing volume? Here or here? Okay. You check, for example, according to this plane, according to this normal, make the scalar product. If it's negative, it's outside. If it's positive, it's inside. This is already a lot to know. Okay? This is something, an idea, in which you can start to base, for example, your algorithms for visibility determination. you say, okay, anything around here is not visible. I do not perform calculation over it. I do not perform shading over it because it's outside my current viewing volume. Viewing volume, center of projection, and this is my viewer. Okay. As long as the viewer moves, the viewing volume moves, and this point might find itself inside the viewing volume, and this outside the viewing volume. At every modification, of viewing modification, change of position of the viewer, I have to re-perform this calculation to understand, is Q in the viewing volume or is Q outside the viewing volume? It's something that you do very often to decide what to draw and what not to draw. With this technique, well, a simple scalar product of the point against the normal of the plane, it's very easy to understand if a specific point is inside or outside just by taking the sign of the scalar product. And that's good. That's good news. So RGB PC. And the last step, so what do we need as a plane? Well, information that we need is the normal and P0, right? But since D is equal to minus the normal scalar P0, either we have the normal and P0, or we have the normal and the coefficient D of the Cartesian equation. Therefore, you can indicate a plane as a vector, as an homogeneous vector, made up of 4 components. The first 3 components are the components of the normal. The fourth component is the coefficient D. If you think this as a vector, A, B, C, D, with 4 elements, then you can write this equation, which is the equation of the plane, n scalar Q plus D equals to 0, without using the addition. Let's say that this vector is called L, the homogeneous vector. Then you can write the equation of the plane, instead of using this addition, which kind of breaks our balls, just like this, with the scalar product. L scalar Q equals to 0, whereby L, I intend a special vector, which is made up of all the components, A, B, C, and D. A, B, C of the normal, and D of the coefficient. So, a point Q lies on a plane. If given the vector L of this plane, it results that its scalar product with Q equals to 0. The sign of L scalar Q gives me the information if that point is outside the plane in the positive side, outside the plane in the negative side. So that's it. Now that you know how to write a ray and you know how to write a plane, it can be interesting to perform an intersection between a line and a plane. Why is it interesting to intersect a ray with a plane? For example, in ray tracing, we see that with ray tracing, we cast a ray in the space and we hope to hit something, right? But what does it mean, hitting something with a ray? It means that there exists an intersection between a polygon in the scene and the ray I have cast. So I need to know how to create an intersection, at least for the moment, between a plane and a line, a plane in which the polygon is belonging to, and the ray which I am casting during my rendering algorithm. So you take the plane, it's over here. You take the ray, it's over here. You plug in the ray inside the plane, like this, and you get this equation. Now it's straightforward. You just solve to look for the value of the parameter t for which this equation holds, for which you have the intersection. You find it like here. This way you find the value of parameter for the intersection. You plug it back into the ray, and you have the coordinates of the point of intersection. Do you see it? Well, it's easy. I'm just saying that this is the plane, but P is actually expressed in parametric form along a ray. So it becomes like this. But since P dt is this, it's n scalar q plus n scalar v, parameter t plus d. Shuffle everything, you get this. This is the value of the parameter in which you have the intersection. As simple as that. Good. Well, these things I actually already explained. This is to remember you that when we're dealing with vectors, if this is my point or my direction, v1, v2, v3, so here, v1, v2, v3, well actually, I'm sorry, if I have the point over here, which is alpha, alpha 1, alpha 2, alpha 3, I always have to remember that this alpha point or alpha value is always expressed against a set of coordinates. In this case, v1, v2, v3. That it really means that the complete definition of this vector is always made up by its coordinates, alpha 1, alpha 2, alpha 3, against a specific basis, v1, v2, v3. This gives me the idea that the same object, the same point, the same vector, I could actually represent with different sets of coordinates. I mean, the same point could be 1, 1, 1 in the x, y, z coordinate reference, but could be 3, 2, 1 in a different set of coordinates. The point might be the same in reality, but if I'm changing the coordinates, the set of coordinates, its coordinates change as well. This is what we call a transformation. Oh, here there is a problem, of course, that when you're actually referring to coordinates, we do not only need the vectors, v1, v2, v3, to form an orthonormal basis, but we need something more. We need the point of origin. Where do these three vectors start? So it is true that we need a vector basis to form a set of reference of coordinates. But along with the basis, we also need the reference point. In this picture, you see the difference between using a coordinate system without using a reference point and using a coordinate system with a reference point. As you can see, there is a certain difference in concept. If you put together the idea of the basis plus the reference point, well, a vector basis plus a reference point is called a frame. Not to be confused with frame in terms of, well, refreshing the screen every so many times per second, a frame per second. It's not that frame. It's not a representation of the screen in a specific moment. Here, a frame is intended as a term, as a geometrical entity made up of a set of vector, which is the basis, plus another vector, which is the reference point. So, every point in a frame can be described as that. its coordinates against the bases. So alpha 1, alpha 2, and alpha 3 against the base v1, v2, v3, plus the point of origin. This is everything you need to pinpoint a specific point in a system of coordinates. So we need that point, because otherwise we don't know from where to start to count. We know the directions. This is what the basis is for. But we don't know the measure, from where we start to count distances. That's why we need P0 as the origin of the frame. But this P0 breaks our balls. Because here I have nice multiplication of terms. And here I have one vector which is just summed to the other multiplication of terms. So if I want to change from one basis, from one reference system to another reference system, I have to do two operations. The first operation is to transform the basis. The second operation is to translate the reference point. So, virtually, well, in practice, it is two operations that I have to do. I can multiply, as you can see, the current base v1, v2, v3 by an orthogonal matrix to obtain another set of coordinates. In this way, I can transform, that is, change the orientation, the nature of the coordinate system. But that does not change, along with it, the reference point. I would like to be able to do this in one single operation, in one single transformation. To do this, I need not to stay with three coordinates, but I have to use homogeneous coordinates. We use them already, homogeneous coordinates, to differentiate between directions and points. Here, we use them to consider in one go not only the three vectors of the direction of the vector basis, but also the reference points. Consider, if we define two operations for the frame like this, a point scalar 0 equals to 0, and a point scalar 1 equals to p, then you could represent this, p equals p0 plus alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3, as just one single matrix product. So you see, once again, we understand why a vector which represents the coordinates of one point in a space has the fourth coordinate as 1. You see? If you put the fourth coordinate of the point as 1, and you put as the fourth vector for the frame the reference point P0, then you can represent any point P in that space, where alpha 1, alpha 2, alpha 3, 1 is the homogeneous coordinate of the point. V1, V2, V3, P0 is the frame, that is, the base composed by the three vectors, plus the vector which gives the reference point. Now, that's already something. If we consider homogeneous coordinates and frames represented as a vector containing vectors of bases and reference points, then we can change not only from one base to the other like we did here in the 3×3 matrix, but we can directly change from one frame to the other with this system. we can go from V1, V2, V3, P0, which is one reference frame, to U1, U2, U3, Q0, which is a different reference frame. That is expressed the same point in space with two different set of coordinates arranged according to different frames. Can you imagine that? So, we can pass from one frame to the other thanks to a matrix over here, a matrix which is 4 by 4. This is the general form of the matrix. To go from B to A, you actually have A equals transpose of that matrix to B. Therefore, you have the transformation matrix, which is this. This is the general form of the transformation matrix over here. In this transformation matrix, you always use this part to translate the coordinate system, and you always use this part to translate the rotation. Look, it was not clear. This one is used to transform frames. This one is used to transform points. You see? You invert your point of view. This is subtle. It needs a couple of showers and a few hours of toilet sitting to understand that. But changing frame is like the other side of the coin of moving the points. Look, I am taking a picture of Monica Bellucci, right? And she's a little bit to the right of my frame. I have two options. I want Monica Bellucci to the left of my frame. Option number one, I move myself to the right, so Monica Bellucci, which doesn't move, appears on the left of my frame. Or I can ask Monica, move a little bit to the right. Okay? You can either move the point, that is Monica, or you can move the reference, which is your camera. This duality is given here. If you are operating on frames, you operate like this. But if you want to operate on points, that is the point of coordinate A and the point of coordinate B, then you have to transpose this matrix. So this matrix over here is the one you use to when you think about moving points in the same frame. And this matrix here is when you think to keep the point still and moving the frame. In the first case, you move the point but keep the frame. You keep your frame intact and change the coordinates. Let's make an example of moving. Well, did you already do with Raffaella transformations in OpenGL? Or not yet? Yes or no? No? Okay. Well, you will see that OpenGL has the same concept. You can, well, in OpenGL, you can refer to the camera frame or to the world frame. That's the same thing. If you're thinking your transformation on the camera frame side, what you're doing is that you're moving the frame to perform a transformation. If you're thinking a transformation in the world frame point of view, then you think your frame are fixed and you're moving your points. But it's actually the same thing. Let's see how you make transformations. You see, we are using the matrix we are thinking the transformation, let's think the transformation in the word frame. So let's think that we are moving points according to the frame. If you are moving points according to the frame, then you have this part here for translation and this part here for rotation. So this is the general representation for a translation transformation matrix. If you want to translate a specific object, you translate it of a distance with a direction. That is, you apply a displacement vector d to every point of that object. This displacement vector has to be put here. Ax, Ay, Az. This is the displacement vector. This is the general equation. This is the resulting transformation matrix. What if you want to do a rotation? Well, rotation is a little bit more complicated. We go to trigonometry here. If we consider x in polar coordinates, you remember polar coordinates? It's r cosine phi, y is r multiplied by the sine of phi. Let's consider that we rotate an object around the z-axis, like in this example over here. This is the z-axis. This is the rotation you perform. When you rotate, you are actually adding an angle theta to the current angle phi. So the new position of all your x and y, given that the z doesn't move because you are rotating around z, is the same polar coordinates representation plus the theta, which represents the angle of the degree of your rotation, in degrees of your rotation. You can use trigonometric identities to separate the x and y contribution. This goes to rho cos phi cos θ minus rho sinus phi sinus θ, but you see that rho cos phi is x, rho sinus phi is y, so you can rewrite it as x cos theta minus y sin theta, etc., etc. Same thing from y over here. So these are the coefficients, cos theta minus sin theta plus cosine theta, that you can put in the transformation matrix for rotation around z. So these are the coefficients for rotation around z. These are the coefficients for rotation around x. These are the coefficients for rotation around y. As you can see, this is a simple rotation, so you do not have anything on the displacement vector over here. So this matrix just rotates every point in your frame. Scaling. You can scale with different factors along x, y, and z. And you put the scaling factors on the diagonal of the transformation matrix. If you put 1, 1, 1, of course you don't scale anything. If you put 0.5, 0.5, 0.5, you are reducing to a half according to each one of the axes, proportionally. You can also make unproportional scaling, like for example 1.51. It means that you are scaling only along one axis. So you can really make some combination of scaling, reduction, or enlargement. You have an enlargement. Instead of putting a value between 0 and 1, you put, for example, 2, then you double the size of that object along that axis. So these are the three basic transformations: translation, rotation, and scaling, with their matrices. You can combine them. You can concatenate transformation. So you could think of multiplying these matrices. For example, you could use a translation matrix and multiply it with a rotation matrix. What you would have is that you would have here the rotation part, and here, instead of 0, you would have the translation part. This single matrix would do in one multiplication, rotation and translation, or roto-translation. But what is the order? First the rotation or first the translation? Or first the translation and then the rotation? Because the result is different. I mean, if you rotate and then translate, the object ends in one way. If you translate and then rotate, the object ends in another way. When you're thinking this in object coordinates, so the frame stays fixed and you're moving the object, it becomes very clear. I mean, you translate and you rotate, or you rotate and you translate. Okay? You get different results. What is the order of transformation? The order of transformation depends on the order you used for multiplying together the basic transformation matrices. More specifically, the order of transformation, real transformation of the object, is the inverse of the order of multiplication. So if you want to rotate and then translate, what you have to apply on the object is a matrix which is obtained by taking the translation matrix multiplied by the rotation. In this way, you first rotate and then translate. It depends on the way you are applying here the transformation in the pipeline. So if you want to do first transformation A, then transformation B, then transformation C, then your matrix should be CBA. Why? Because first you do this. What is it? My pointer. You see it? Here it is. First you do this. Then second you do this, and then third you do this. Okay, I think we can take a small break, and we will start after the break with visibility determination. Okay, let's start again. Please, let's start again. Mi fate chiudere la porta, per favore? Ehi! Mi fate chiudere la porta, per favore? Grazie. Okay, the topic of this lecture, which is actually the topic of today's lecture, we are half lecture behind schedule, actually. Visibility determination is an introduction to techniques which you need if you want your computer graphics engine to have an efficient performance in rendering. Well, I'm actually not going into the gory details. By gory details, I mean by showing you all the blood and all the suffering. But it's more than explaining the basic terminology, the general methodology, and just to give you a hint of the suffering and the blood, I have a couple of numerical examples, but not on everything. So most of the lecture is rather general, so going through the basic ideas. If you want to really implement them, then of course you have to refer either to the internet or to books or to specific algorithms. But at least after this lecture, you know what you should be looking for. And I added a couple of numerical examples just to give you a taste of the complexity of the problems, even if they seem trivial at a first glance. By trying to solve them practically, you understand that they are not trivial at all. So just to name a few of the basic methodologies that you might want to look at, to study, we have transformations of coordinate systems. That is, we tend, before applying a specific calculation or specific processing, very rarely we apply this processing by staying in world coordinates or frame coordinates, so to speak, with OpenGL. Very often, before doing specific operations, we prefer performing a change of coordinates, a change of reference sets, in order to perform more easily some sort of processing. For example, clipping. Before performing clipping, and that's the second point, clipping strategies. What is the idea of clipping? The general idea is I don't want to process things that anyhow will not be shown at this moment. So I want to cut away everything which is useless in this specific situation. So if I'm focusing and visualizing this area of the scene, I'm not interested in all the polygons which are making up the blackboard, the curtains, the lamps. I don't care about them. I want to cut them away. That's actually called culling. That is, I cull away, I take away those parts which for the moment are useless. So no need to feed them in the pipeline for, I don't know, transformation, shading, texturing. It's useless because anyhow I'm not going to visualize them at the current stage or with the current position of the viewer. There is something a little bit more extreme, which is called clipping. The idea of clipping is that you have some kind of mesh, some kind of shape, and the situation of your viewing volume is such that, let's say, part of this shape is inside the viewing volume, the other part of this shape is outside the viewing volume. So if you're applying a culling strategy, what you actually would do is to delete the complete object from the scene, even if actually half of this object is actually in view. This could be acceptable. This could be unacceptable. It's up to you and the specific application you're developing your engine for. So I'm not saying that every time, everywhere, for every engine, you have to apply clipping strategies. I'm just saying that you have to be aware that for some time, in specific situation, culling might not you want to be, because you're not precise, because actually part of that object is inside and part of that object is outside. And you might want the degree of precision to represent this. If you want this degree of precision, then you need clipping. Clipping is actually cutting the object in two parts, the part which is visible and the part which is not visible. Once you have clipped the object in two, then you can cull away the part of the object which is outside the viewing volume and keep and render the part which is inside. We will see two clipping strategies which are performed at segment level. At segment level, it means that you apply a test for clipping for every segment which makes up a polygon. So it's actually a very fine technique which is used for engines which are performing very precise, specific visualization. For example, medical imaging could be an application. You cannot afford to clip away an entire part of the brain because it's inside a single data structure, part of it which is outside the viewing volume. So you need to represent accurately all the data, yet in an efficient way, so that the surgeon doesn't fall asleep just because he has updated with a couple of, I don't know, moving a little bit the mouse because he wants to see a different angle. So you need the rendering system to be efficient yet precise. So that's, for example, one context where clipping might be useful. By the way, in the second semester, now that I'm talking about medical imaging, we will have one lecture about medical imaging. So I will show you a few examples of CAT scans or MRIs. Do you know those things? Computer-aided tomographies and magnetic resonances. And, renderers, which are called volume renderers, which are able to acquire cloud of data from MRIs and CTs, and the possibility that you have to image that data and represent them in real time, for example, to let surgeons diagnose, I don't know, aneurysms or tumors, or that's rather interesting. Well, not the aneurysm, but the technology which is behind the imaging system, which is kind of cool. So clipping strategy is one thing. Hidden surface removal is another strategy. The idea is, if something is hidden behind something else, then I can safely cull it away. So the idea then is think about strategies to detect when a specific surface is actually hidden from view because of an occlusion by another surface which is in between the viewer and that surface. So if I'm putting myself here, I have an occlusion by the table, I don't see you, so I can safely call all of you away from the scene because I don't need you in my current visualization. That's hidden surface removal. Bounding volumes. Bounding volumes is the technique I was mentioning earlier today. The idea is to put a complex mesh inside a volume, usually a box. Of course, you would need the best fitting box you can think of. Why? Because since you have put the mesh in the box, the bounding box, all your other calculations, for example, visibility tests, are made against the box and not against the mesh itself. Why? Because it's simpler. Maybe the mesh is very complicated with a lot of vertices, a lot of polygons, and you actually just want a test to check how much of that mesh is inside or outside the viewing volume. Well, you could just test the box instead of testing all the polygons of the mesh. Of course, the better the box is fitting the mesh, the more accurate is the test. Here we talk about bounding volume instead of bounding box, because you could think of different shapes for bounding your mesh. The box is the simplest one, but you could think about bounding spheres or bounding cylinders, which are also suitable techniques. Actually, more sophisticated engines, for example, this is a technique which is very often used in game engines, about gaming, when you need a fast response, but accuracy usually is not very much an issue. You actually take your gun, start shooting around. If you more or less hit the enemy, that's okay. You don't need much of accuracy. You need speed, because the enemy is moving fast, you are moving fast, so most often games trade accuracy for speed. So what do they usually do? They start with bounding spheres, which are very fast to calculate, because, well, a sphere is you just need the radius and the center. You decide the radius, you decide the center, and then you make all your visibility determination tests with the sphere. If the visibility determination test with the sphere fails, then you know that that object is not viewable, is outside. If the visibility determination test tells you that the object might be visible, then most engines recalculate the bounding volume with a bounding box. Why? Because the bounding box has a more probability to be more accurate than the bounding sphere. The bounding sphere is more coarse. They test again with the bounding box. If the bounding box fails, then you can call away. If the bounding box hits, meaning that the object might be visible, then the object could be considered visible, or you could clip it, or you could go and make some finer adjustment or some finer calculation. Is it clear? Because the sphere is big and coarse. If the sphere fails, it means it's really outside. If it hits, then you start with the box. It's still simple, but it fits better. If it fails, then it's outside. The sphere didn't understand it, but the box, yes. If you hit with the box, then either you need something finer, or you surrender yourself and you say, okay, it's visible, and you consider it visible. So you can apply bounding volumes in a row, several bounding volumes with different degrees of coarseness to test the visibility. What actually you have to do, it's up to you and up to your engine. There is no single solution. Every engine makes up the best implementation their author think is the best to obtain a specific scope. So, visibility determination tests, I've been talking briefly about them. Another thing that you can do is how to arrange the scene using spatial structures to optimize visibility determination test. Meaning, you can be even more smart, you can even be smarter than this. Instead of testing against the whole viewing volume, you can divide the viewing volume in parts and just test some parts of the viewing volume. This is what we call octrees. I don't know if you ever heard about them. An octree is a subdivision of 3D space in 8 areas. And you keep recursively subdividing the space in 8 by 8, like dividing in quadrants, in octants, actually. And in this way, you create a tree with information about where certain meshes are against the trees. And you scan the tree looking for objects. Well, this is a little bit quick, but this is the general idea. Organize the object in a tree to scan their position more quickly. This is the idea. And polygonal simplification is actually something that we have been working in our research for some time, but I'm not sure that we will have time to look at this. So I'm not covering that for the moment. Maybe if there is some time left, which I doubt, I will show you a few examples of what we did for polygonal simplification. Okay, well, let's start. This is more or less the topic. There are two broad approaches to processing information in computer graphics. The first approach is called image-oriented approach. The second approach is object-oriented approach. The image-oriented approach. The idea is that what is processing? It's a loop, basically. It's a cycle that your engine makes to cover all the data it has to render. So it loops. Start render, render everything that you have to render. Okay, that's the loop. But what are you basing your loop on? In the image-oriented approach, you loop over pixels. The idea is this. I know already that my frame buffer will be 1024 by 768 pixels. So that on this information, I am basing the main loop of my rendering engine. So start with pixel 1, then go with pixel 2, now pixel 3, pixel 4, pixel 5, until all the pixels are done. This is image-based. You start from the pixel, you loop all over the pixel you have to render in the frame buffer, and you try to determine backwards which polygons might have an influence on the specific pixel you are currently looping on. Fine? This is an image-oriented approach. You need to know in advance how is your frame buffer organized, because you loop over pixels. The other approach for creating the main loop of your rendering engine is the object-oriented approach. In this approach, you do not need beforehand the frame buffer, because you don't loop over the pixel, but you loop over the vertices. You know that you have so many vertices in your model organized in a data structure. You start vertex number 1, calculate, 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 calculate. Decide that pixel number 1022 needs to be red. Second vertex, calculate, 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 calculate. It turns out that pixel number 4 has to be green. Okay? So instead of going from the pixel back to the object, you start from object, from vertices, and you calculate what impact you have on different pixels. Possibly recalculating the same pixel 5 times, 10 times, 20 times, because you have no idea of how each vertex impacts on each pixel until you have performed the calculation. So as you can imagine, you can see that this description is rather broad, but you can understand for yourself that each one of the two approaches have has well, immense implications on the overall organization of your program. So you can decide one way to go, which way to go. Each one of the two ways can give you advantages in the way you write your software and disadvantages in the way you behave. It really depends on the kind of application you have. But basically, in an object-oriented approach, well, you loop across vertices, and this, what does it mean? That potentially each vertex can affect many pixels, possible the same pixels. Any one of the pixels in the frame buffer. This implies, since you start from the vertex and you don't know in which part of the frame buffer you will put your result, it means that you need your entire frame buffer available at all times during processing, at the final size of your display. This could be a problem, this might not be a problem, it depends what are the contexts you are in. But if you are object-oriented, you need all the frame buffer available, from the first pixel to the millionth. In an object-oriented approach, most global calculation, for example, transparency, cannot be performed because you process each object independently. You start with one vertex or with one polygon. You process, you write in the frame buffer. Next vertex, you process, you write in the frame buffer. But you lose the idea, the memory of how the interaction between all the polygons might cause specific visual effects. So you're very local. You're local to the polygon or to the vertex. To globalize this processing, the only way is to have one copy of the buffer for each globalized effect I need. One example of this is the Z buffer. The Z buffer, or depth buffer, is a technique which is used by renderers which have an object-oriented approach to keep a temporary area, a buffer area, to compare the depth of two objects when they want to decide if part of the object is hidden or not by another object. So, what does the Z buffer does? Instead of keeping in the cells the color information, like the frame buffer does, the frame buffer in each pixel takes 24 bits, right? You remember? Why does it take 24 bits? Because it's 8 bits for the red, 8 bits for the green, 8 bits for the blue. 255 intensities for each channel. In this way, you make millions of colors, which is what you want to do. You want to display so many millions of pixels, each one capable of so many millions of colors, on your frame buffer on the screen. That's your normal, well, the video frame buffer. If you want to have some global interactions between the objects, like for example, understand if object A is behind object B in relation to the current position of the viewer, that's already a global consideration. Why global? Because you're considering an interaction between two polygons. The only way to do this, since I am object-based, that is, I am considering one polygon at a time, is I am processing polygon A. Polygon A has an impact to a certain area of the frame buffer video. I perform the calculation, I put the colors on the frame buffer. But I also use a Z buffer, which has the same size of the video frame buffer. And in the corresponding pixels, instead of putting colors, in the Z buffer, I put the value of the Z coordinate. That is the depth This is the z coordinate. That is the depth against the position of the viewer. In this way, when I am finished with object A, and I want to process object B, which is, I don't know, here. So A is already made. B is like this, here. Then you can see that part of object A, which I already processed, should be taken away. But how can I realize this if I am always considering one object at a time? I can realize because I'm saving on the Z buffer the Z coordinate information. So when I'm rendering this part of the polygon, B, and I'm going to put the colors that I calculated on the video buffer, before putting, I go to the Z buffer and I compare the depth of the last object I have calculated with the depth of the current object I am calculating. If it turns out that the depth of the current object is less than the depth of the previous object, then I replace the pixels, the color pixels. Because it means that the object I'm considering now is in front of the object I considered before. Do you follow me? Otherwise, not. You see the problem? It's like we need a set of variables to store the depth of previous objects in order to understand when I'm considering a new object, is this in front or behind? Because if it is behind, who the fuck cares? Right? But if it is in front, then I have to understand that it is in front and trash away everything that I did before. Why? Because the first object is in front. So in the end, in the final result, it's the object in front that I will see, not the object behind. But I have no way to do this if I use an object-oriented approach, because in an object-oriented approach, I consider one polygon at a time. In this kind of situation, the only way out to create the correct result is to create one buffer for any global consideration I want to make. So one global consideration is mutual depth, right? Which one is deeper than the other? So I use the Z buffer or depth buffer. That's one. But there could be many other global effects that I might want to add to my scene, still keeping the object-oriented approach. So I could have an alpha buffer. What could be an alpha buffer? An alpha buffer is a buffer that stores information of transparency between objects. So, for example, object A is opaque, and object B is transparent. So, I'm processing first object A, which is transparent. I put on the alpha buffer the information that there is this color, but there is also this degree of transparency. So, when I am putting the other object behind, and I see from the zeta buffer that it is behind, I might consider looking at the alpha buffer if there is some degree of transparency. And if so, I interpolate the colors. If not, there is no transparency, the object in front is opaque, I do not make any color interpolation. Same thing for the shadows. If I want to make shadows, or you name it, any effect that has a global nature, that is, it implies a mutual interaction between at least two objects, then in an object-oriented approach, you need an additional buffer. Mind you, each buffer is like grids. Okay? I refer to the same information in the same grid. So, if the buffer is 1024 by 768 for colors, 24-bit deep, a zeta buffer or depth buffer has to be 124 by 768 by how many bits I need to store the Z values. You need the alpha, yet another 1024 by 768 buffer. So you see that the amount of memory that you need, I'm killing myself, could be important. Could be important. Is this a problem? Is this not a problem? It depends. It depends. It depends from my hardware, it depends from my application, but me as an engineer, I should be aware of the requirements of such an approach. And ask to myself, okay, I'm just making a game for people that already has anyway, I don't know, a triple video board with, I don't know, whatever, with Pixel Assassin chip on board, and there will be no problem. 500 gigabytes of video RAM, so it's okay. But it could be, I don't know, it's something for rendering on a mobile device, so there is no memory, there are few limitations, so you have to know what you're doing and take into account your limitation. Vice versa, the image-oriented approach. Image-oriented loops over pixels, or rows of pixels, which are called scan lines. And we work backward. We start from pixel 1, we try to determine backwards which are the polygons which have an impact on the pixel we are considering. And how can we do this? Actually, it's a trick, because to be able to do this, what do we have to do? We have to process the vertices, to link them to pixels, and to create a data structure. With this data structure, when we start the rendering, we know to which pixel every object is linked. So we have a pre-processing stage in which we are actually linking the pixels to the vertices. And then the rendering stage in which, thanks to the information that we have gathered in the pre-processing stage, we go from the pixel backward to the vertices. In fact, unless we first build a data structure from the geometric data, we do not know which primitives affect which pixels. So all the geometric data must be available at all times, and you always need a pre-processing time before start rendering. You cannot start rendering right away. Which is the best approach? Well, again, it depends. But I can tell you that the most widely used approach today for games, for whatever, is the first one, the object-oriented approach, in which you have several buffers that you have to keep in memory to render. The programs that you are starting to make, did you start, I don't know, making rolling cubes or spheres or something like that? Did you start doing something? Drawing something? No? Yes, you did. Well, the rotating cube? No rotating cubes yet? Okay, we will make your cubes rotate as soon as possible, don't worry. All the approach that we will use with our examples in OpenGL is object-oriented. It's not image-oriented. You will see no pre-processing linking the geometry to the pixel. We will do everything looping through the vertices and rendering to the pixels. So everything we will be in the object-oriented way. Good. That are the two basic approaches. Either way, you have to solve four main problems in a rendering engine. Well, modeling is decide a way to represent the geometry of your problem. Geometric processing is determine which of these objects are to be visualized. This includes normalization, clipping, HSR, hidden surface removal, and shading. Shading is calculate the candidate color for the polygon. Calculate the color for the polygon. When you have done all this, you do the last part of the geometric processing, which is projection. Projection is passing from 3D space into the bidimensional space. Mapping from 3D into 2D, because for the moment, anyhow, you are visualizing the result in 2D. We have no widely spread 3D monitors at the moment, so we still need to do projection. After projection, you have rasterization. Rasterization is when you convert the polygons in pixels. That is called also scan line conversion. And then you display. You do not do it, it's your driver and your video board that does the display. Yes? No. Okay. One of the first steps, as I told you, in geometric processing is handling the transformations. What do engines do usually when they are processing? They actually continuously change the way they represent coordinates internally. When you are feeding the engine with the data model, that is the list of vertices and polygons composing your scene, you specify object coordinates, world coordinates. So you're working with a modeler, be it 3D Studio Max or Blender or Maya or Vermal, and you draw things, you shape things, you create your 3D model, and while you're working with your drawing tool, you're configuring coordinates, setting coordinates. All these coordinates are object coordinates. So object coordinates, which is the result, as you see there, from the model activity. From these coordinates, usually the engines transform these coordinates into camera coordinates. That is, recalculate all the coordinates according to the current position of the viewer. So the viewer moves, and every time the viewer moves, all the coordinates which are expressed according to the specific object are recalculated on the reference made up by the position of the viewer, the direction in which the viewer is looking. That's called the viewing transformation. Look, when you're modeling, for example, you're modeling this PC. So you say that this is vertex 1, 1, 1. This is vertex 1, 1, 2. Okay? So you define putting all the coordinates of all the vertex of the 3D object, but according to which reference system? To the reference system of your model. But then your model starts to get alive inside your engine. And you start viewing it at all different angles. What do the engine do? Every time the viewer changes its position, it has to change all the coordinates. The approach is that it changes the coordinate, transforming them into the set of coordinates of the viewer, which starts from the center of the viewer with the direction of the viewer. The model coordinates were used to model. But as soon as you start viewing it, you don't need the model coordinates anymore. They are the starting point, but from them, you need to recalculate everything to take into account that you look at that model from different points, from different positions. So you recalculate everything with a different set of coordinates, which are the camera coordinates, or eye coordinates. Once you do that, you perform projection and normalization. With the eye coordinates, you take into account the position and the direction. But you need to take into account another thing, that your viewer could be a perspective viewer or an ortho viewer, an orthogonal viewer. You remember the difference between a perspective projection and an orthogonal projection? It really changes the way your final projection looks like. In a perspective projection, all the projectors are converging in a point in the finite, which is the center of projection. The effect is that your coordinates change according to the fact that your viewer is getting nearer or further away from the object. Because you have a convergence of the projectors to the center of projection. We have seen it last time, I'm sure, I remember it very well. In your orthogonal projection, all the projectors are parallel. They converge, but to a center of projection which is to the infinite, because they are parallel. These two different ways of projecting, with converging projectors or with parallel projector, give you a completely different result when you project on 2D. There is a specific transformation matrix, which is called the projection matrix, which transform eye coordinates in projected coordinates. Namely, what happens during the projection transformation is that if you have a perspective viewing volume, such as this one, you have a perspective viewing volume, like a cone. The projection transformation always transforms the viewing volume into an orthogonal one. This means that, well, the position of certain points will change, because when you are perspective, your volume is like this. The normal projection rearranges the points in order to have an orthogonal view of it. Why do you need the orthogonal? Because you like very much that these planes are all orthogonal and the normals are all orthogonal, because this simplifies a lot the algorithms. It's way better than having planes with normals which are done like this. Do you agree? So this is actually the meaning of doing a projection transformation when you have the eye coordinates. So you go to eye, and then you perform a projection to transform a perspective viewing viewing volume, into a orthogonal viewing volume. Still, you're not happy, because another thing you do is a normalization. That is, you remap all the coordinates in order that you have the size of this cube all equals to 1. In a way that you can express all coordinates with a number that goes from 0 to 1. This is called a normalization. When you have remapped your space from object coordinates to eye coordinates which take into account the position of the viewer, projected it into ortho if you were perspective, and normalized the viewing volume in a way that you have 0, 1, 0, 1, 0, 1 as sides, then you find yourself in a coordinate space which is called NDC. which is normalized device coordinate, which is a system of coordinates which is not dependent from any device, and it is normalized. I'm sorry, I see the suffering in your faces, but without the basic, it's really impossible to understand any technical literature about these things. So we have to go through it. I think I have a picture here. Yes, you see? This is what projection does to the viewing volume. It goes from perspective to ortho. And that is what normalization does. If your ortho volume is like this, normalization centers and normalizes it. So it gives 1, 1, 1. Well, it depends the kind of normalization you want. This is actually a side of 2, because it goes to -1 to 1. But it has the nice thing that it is centered. So it depends. You can choose the normalization you feel more comfy for your algorithm. Then it's not finished, because after you have norm coordinates, NDC coordinates, then you want to go to screen coordinates. To go to screen coordinates, you flatten all z coordinates to 0, and then you have to map your bidimensional space to a specific position on your final screen. Those are the screen coordinates. That is, the coordinates on the screen where you're going to do the visualization. That depends from the size, vertical, and height of your screen, which is something that you do have to declare, for example, in OpenGL. Did you do the visualization callback in OpenGL already? I think yes. You opened the window. And since you opened the window, you were forced to specify if it was a perspective or an ortho, right? And you had to specify, well, either the aspect ratio or the dimension of the window, the height and the width in pixels. Why do you need that? Because you need to map the three-dimensional space normalized into screen coordinates. Well, not you. OpenGL does it for you. But this is why he needs to know where he is going to. Right? Okay. Oh, as I said, well, I could stay here for hours and explaining every little gory detail, but I'm sparing it to you, really. There is no, this is just the interpolation formula, and it's nothing much interesting. So, mind you, okay, this is the whole process of changing of coordinates at every step. At a certain point, before going to screen, here, you're ready to perform clipping. Why here? Because now you have a nice little cube centered in the origin with known dimensions, either 1 or 2, which is like having a fixed window against which it is much easier to determine if a segment is inside, completely outside, or partially inside or outside. That is, making this kind of considerations. To preserve your sanity, that is, to avoid that all of you run away from the room screaming and tearing your shirts, I'm not handling clipping at 3D level, I'm handling it at bidimensional level. The texts say, Once you know bidimensional clipping, it is very easy to go to three-dimensional clipping. Bullshit. It's difficult. Because it's difficult already in 2D. And in 3D, it's even more difficult. But let's start and try to understand what are the intricacies of something which seems so trivial, like understanding if this specific segment, look, this is our viewing volume, you see? We are back to 2D for simplicity, but the idea is that we are at the end of normalization. We have normalized it to ortho. Possibly we have normalized the coordinates, so better still, this could be a square and not a rectangle. Okay? But it really depends. But this is the viewing volume against which I am trying to perform visibility determination. That is, my question is, this segment has a side of a triangle, the triangle being a polygon, the polygon belonging to a mesh, right? Is inside, outside, or partially inside or outside, or even a little bit outside, a little bit inside, a little bit outside. There's no limit to evil, you see? We have to understand this, but not just looking at it, because it's easy for us. This is outside, this is inside, right? But how can I do an algorithm which decides this in the most efficient way? This is the clipping problem. So let me present you two different methods to face the clipping problem in bidimensional space. The first method is called the Cohen-Sutherland method. Cohen and Sutherland propose this approach. Look, there is one approach which is very basic. I mean, without Cohen-Sutherland. Okay? These are four lines of which you know the equations. Okay? This is x equal to a1. This is x equal to a2. This is y equals to b1. This is y equals to b2. Then you have the xy coordinates of each one of the points. You start intersecting all the lines. Okay? This one intersects with this, this, and this. Then this one intersects with this, this. You have to calculate. Well, in the worst case, there is one intersection, two intersections for each segment. Well, no, you have to test for 4 intersections for each segment. Okay, because you have four lines. So it's 4, 4, 4, 4. It's already 20 divisions that you have to do to check for intersections over here. You could do that. But what you want is performance. And division as an operation and performance are two words that don't stay well together. Okay? Every time you want performance, you want to avoid making a division, particularly if it's a useless division, like in this case. Okay? You're making 4 divisions to look for 4 intersections. In all 4 cases, useless, because you don't have any intersection here. So you lose a lot of time. So that's why we need some more ingenious approach, some more smart approach, with our goal in mind for performance, to make as less as intersection tests, that is divisions, as possible. So first method, Cohen-Sutherland. Cohen-Sutherland allows to execute the calculation for intersection only where this is in fact necessary. So the smart thing is, first, you determine if there is a possibility that there is an intersection. If there is, you calculate the intersection. Otherwise, you discard the segment because you know already that there is no intersection before starting making the division and realizing that there is no intersection. So you avoid wasting time, which is good for our engineers. So this algorithm gives you a big advantage if the general situation of your engine is that most of the segments are outside the clipping window. You just have to determine which are inside or which are partially inside or outside and create an intersection on them. How do you do that? Well, you assign a code made up of 4 bits to different bidimensional regions of space, specifically this one. Here inside, I'm making it bigger, this one here is my clipping area, my viewing volume. Okay? So inside the viewing volume, the code is 0000. Each bit has a number. The first bit is bit 0. The second is bit 1. The third is bit 2. And the fourth is bit 3. We count 0 based because we are computer engineers and we like to complicate things. So the first is 0 and the fourth is the third. Right? You know that. That's called 0 based calculation. A 0 based array. You put the first bit, that is bit 0, to 1 if the y-coordinate of that region is greater than the maximum, the y-max of the clipping area. So this is y-max, this is y-mean, this is x-mean, and this is x-max. If the point you are considering in the area you are considering has a y-coordinate which is greater than y-max, which is over the clipping area, then you put bit 0 to 1. In fact, in all this area over here, bit 0 is to 1, you see? You go with the same rules. Well, if y is less than y mean, if x greater than x max, put 1 to b1, b2, or b3. So you can see that being to the left, so to speak, is the last bit, you see? Being to the top is the first bit. Being to the right is the third bit over here. And being to the bottom is the second bit. Okay? And the intermediate position, mixed. So since this is to the bottom and to the left, it has the second and the fourth. See? So it's just a way of flagging areas. But if you flag the areas in this way, then you can devise a set of rules to understand if your segment is completely outside, completely inside, or partially inside or outside. Why? By just comparing the outcodes of the endpoints of your segment. Okay. Your segment is, like for example, here it is. So your segment is like this. So you have two endpoints. This is one endpoint, and this is the other endpoint. You see? This endpoint has outcode 0000. This endpoint has outcode 1010. The idea of Cohen-Sutherland is determine the outcodes of the endpoints. Apply the Cohen-Sutherland rules to the two outcodes and decide if it is an all inside, an all outside, or a partial inside or a partial outside, without making any intersection. What are these rules? If outcode 1 equals to outcode 2 and they are both 0000, It means what? That both endpoints are inside the clipping window. The segment is sent directly to rasterization. You can't do clipping because all the segment is inside. This is the case in which you start here and you finish here, and both outputs are 0, meaning that the segment is completely inside the clipping window. This is the simple case. Then you have that one outcode is 0 and the other outcode is different from 0. It is this case. You have one outcode 0 and one outcode not 0. It means that it starts from the inside and it finishes in the outside. Here is a segment CD because it's segment over here. Right? The outcode, which is different from 0, indicates which edge or edges are crossed by the segment. So you just read the bits. The bits, which are to 1, tell you where are the intersections. So you know that there is an intersection, and you already know where. So you don't even need to make 4 tests on the 4 sides to look for the intersection. You just know here, you see, that you're intersecting with the top, because you have the first one, and with the right, because you have the third one. So you just make 2 intersections, 2 divisions with 2 intersections, and you will be sure that you will find this coordinate and this coordinate. You already know that the first one is on the top, and the second one is on the right. Okay? You see how it works? Calculating this output is very easy because you just compare the coordinate of the endpoint with y max, y min, x max, and x min. You don't make any division for do that. You just make some comparisons, right? There are differences. So I will spare you the other rules. You can read them. But the technique is smart because by just marking in an intelligent way the space, you can have very useful information to limit the quantity of divisions, of operations you need to do. That's a smart thing. I mean, I know that this approach, you will not be using it to purchase, I don't know, you go into a salami shop and you apply the Cohen-Sutherland clipping to buy some salami and eat in the evening. Okay, it's not the thing you need. But I lose my time, well, I invest my time in explaining it to you because I like the idea. I mean, it's smart. And it might inspire you in solving different problems. I mean, not specifically the clipping problem, but you could encounter in your life different problems that you might not know how to handle. This could be one way. Where was the ingenious way to mark specific situation in a significant way? The other nice idea is that they used bits for marking, so they could express the rule with logical ANDs and logical ORs, bitwise ANDs. ANDs. ANDs, not ANDs. So you could read on and you will see. So this is one method. Well, after you have determined on which side you have intersections, then you can easily calculate the intersection in the usual way. I mean, this is nothing, this is algebra. There is nothing special. What is the problem here? That you have a few problems with parallel lines which are parallel to x min, x max, y min, and y max. With this system, those you can handle. You cannot handle. So, that is one problem. The other big problem is that you make divisions to calculate the intersections. Cohen-Sutherland is good because it allows you to avoid performing divisions always. You perform divisions only when you know that there will be an intersection. But you perform the division to find the intersection. The line bar clipping is even more extreme. You find the intersections only where there are intersections, and you do not perform divisions to find the intersection. So this is really for extreme performance. You don't use division. You just use comparison to find not only if you have an intersection or not, but even to find where it is the intersection. The method is a little bit strange. I think that Lang and Barsky actually were at a difficult point in time of their lives with no women and nothing else better to do. So what they used to do is gathering at Lang's place every evening for several evenings for several months until they devised this thing that I am now proud to present to you. Okay, the idea is to start from a parametric representation of the lines. Given P1, x1, y1, given P2, x2, y2, you can represent each segment with a couple of equations, because it's in 2D, yes? So x is going this way, y is going this way. And if you want to represent as a vector, you represent it like this. You see, this is the parametric form, where alpha is the parameter, nothing new, right? You just rehandle it a little bit, and you express it as P1 plus delta P alpha. Alpha is still the parameter. Delta P just means P2 minus P1. P2 minus P1, it's the difference between two vectors. It means that behind, in reality, there are two equations. The equation for x and the equation for y. Right? This is easy so far. Now, this is where they had the brilliant idea. For every point belonging to a segment, which is inside the clipping window, you can these equations. These equations hold. x1 plus the x parameter is between x min and x max. For each point which is inside the clipping window, mind you. So there is always a delta x alpha, for which, starting from the first endpoint, you can be inside x min or x max. There is always a delta y alpha, for which, starting from the first endpoint, in the y, in the direction of the y's, you are between y min and y max. This is still pretty easy. You can understand. You reformulate again, you shuffle around a little bit again. Considering these four situations, you can write this equation. When you're considering the running x is the x that you're moving along the line, equal to x min, this holds. Minus delta x alpha is always less or equal than x1 minus x min. It derives from here. You can write it for short. P1 alpha less or equal than Q1. P1 is, of course, minus delta x alpha, minus delta x, and Q1 is x1 minus x min. It's just a reformulation. You do the same considering the running x over x max. You do the same considering the running y over y min. And the same again considering the running y on the y max. In general, you always have that pk is different from 0 And you have a parameter which is called alpha k, where k is one of the 4 situations, which is given by qk over pk, where q1, q2, q3, q4 are defined as such, p1, p2, p3, p4 are defined as such. Delta x is x2 minus x1, minus delta x is x1 minus x2, right? And so on. Okay, this is just a rearranging, preparing for the battle. What is the idea? Here you have x min, here you have x max, y min, y max. When you're saying, considering the running x over x min as the position A1, I'm actually pinpointing A1 over here. So this is A1, that is the position on the line given by the parameter running x over x min. So A1 on x min. This is what happens on A2, this is what happens on A3, and this is what happens on A4. See? A4 on y max. So this is this part of the rearrangement on the picture. We position A1, A2, A3, A4. Now look, you see on the picture what happens. That probably contrary on what you were thinking, A1, A2, A3, A4 are not on a subsequent order on the line. Okay? Because probably you were thinking, I put on the line A1, then I put A2, then I put A3, then I put A4. In this order, right. But they don't fall on the line on that order, you see? A1 is here, but A3 falls before A1. A4 falls before A2. Why? Because of the way the line is disposed against y max, y min, x min, x max. Here is the idea, you see? In recognizing that there is a specific order along the running parameter in which these 4 situations are ordered. Now maybe you try to understand where I'm going to go. I'm going to compare, find out algorithmically which is the order on which A3, A1, A4, A2 fall on the line along the direction of the running parameter, which is from here to there. You follow me? Look, if I have another example. In this case, you see, I have A3, A4, A1, A2. It's a different order. Why? Because the line has a different position in relation to the clipping window. So this order matters. This order represents the mutual position between the segment and the clipping window. See? Here is like this. A3, A1, A4, A2. Here is like this. A3, A4, A1, A2. Right? So, the position matters, and it gives you the order of the cases. Now, these are the AKs positioned in this case. Then, you remember that we can calculate the PKs and the QKs. Lyon and Barbieri tell us, if you calculate the PK, and it turns out that PK is less than 0, it means that this AK is moving from the outside toward the inside of the clipping region. It is an in. If the PK is greater than 0, it means that you are going from the inside toward the outside. It is an out. So, this A2 over here, it is an out, because in the running direction of the parameter, it goes from the inside to the outside. So, A2 is an out. Its PK is greater than 0. If you see how PK for 2 is defined as delta x. This is why it's greater than 0, because this is x2 minus x1. x2 minus x1. x2 is over here, x1 is over here. So x2 minus x1 is greater than 0, it means it's an out. And this is true because A2 is in an out position. It's going from the inside to the outside, over here. A4 also is an out. It's going from the inside to the outside. A1 is an in. It's going from the outside to the inside. A3 is an in. It's going from the outside to the inside. You see? This is the inside. This is the inside. This is the outside. This is the outside. Look, it could be different, huh? This is a different example. You have A4, which is an out, A1, which is an in, which is different. It really depends from the position. So it's not always true that A4 is an out. It depends. Here is an out. Here is an in. Here is an out. Wait. Out. In. Oh, they coincide this time. No, but it's... Yes, because it's just the position. Okay. It's just the position. Now that we have decided this, you have to decide which is the winner between the ins and between the out. Who is the winner? The winner for the ins is the maximum between 0 and all the alpha k for pk's which are ins. The winner between the out is the minimum between 1 and all the alpha k's which are outs, for each k which pk equals to 0. So you apply a maximum between 0 and the ins, a minimum between 1 and the outs. And you determine who is the winner between the ins, alpha k in, and the winner between the outs, alpha k outs. Now we are almost finished. If it turns out that the parameter of the winner in the ins is greater than the parameter winners in the out, it means that the segment is completely outside the clipping window and can be simply called. How can you perform the comparison between these without make the division? Because you actually can compare them by multiplication by using the common denominator. Now I will show it to you. Only when you have determined if the division is necessary, you perform the division if you want, if it is altogether necessary. Let's make an example over here. This is the segment, A and B. This is the clipping window, x min, x max, y min, y max. You calculate the pk's and the qk's. And you determine from the p's and the q's which are the ins and which are the outs. Then you calculate the alpha ins and alpha outs, like the maximum between 0 and all the ins. It means between 0, the in here is 19 and 13. The alpha, I forgot to tell you, is qk over pk. Well, I told you over here, but I didn't repeat it. So the alpha, which you are calculating here, is qk over pk. So you are getting the maximum between 0, 2 over 19, because the q here is minus 2. No, it's an in. Q in P1, Q1, yes, is minus 2 over minus 19, so it's 2 over 19. And the other one is 1 over 13, because the other in is 3, so it's Q3 over minus 13. So actually this should be minus 113. There's a mistake here. Huh? Then you see, how do you perform the comparison without making the division? It's easy, because you multiply this by 13 and you multiply this by 19. So you can compare 26 over 247 with 19 over 247. So you actually compare 0, 26 and 19. So the maximum is this one, 26 over 247, which is P2, which is where your intersection, which is P2. Okay, so you have done this without making division, only multiplications. The same thing with alpha out. Then you compare the two, alpha in and alpha out. It turns out that alpha out is greater than alpha in. This means that clipping is needed. Where clipping is needed at alpha in, which is 26 over 247, and at alpha out, which is 152 over 247. This is the position of the parameters with two intersections. This is the parameter. Now you have to plug it in back into the equation over here, and you find the two intersections. I told you that it was a difficult period in their life, and they had nothing else better to do. No, really. But the reason why I'm explaining this again is to let you know that really there is the possibility to devise apparently complex methods, but then it turns out very easily to implement them in an algorithm. This is very easy to implement as an algorithm. Well, the concept is a little bit complicated, but the implementation is straightforward, and the performance is excellent. So I just wanted to give you an idea of, well, I said earlier, the gory details, the blood and the suffering, is even in things like this. I mean, trying to sort out an algorithm to solve a problem which is apparently simple, but as you see, it is not. Okay. Let me know if you can master the method. It will be a good exercise for your geometric capabilities. It's also a training for your mind to start x2, x1 minus greater. So what is the geometrical meaning? You have to start thinking, squeeze your mind over it, because this will enhance your capability to understand, to see through the numbers the reality of the geometry. If you will never try to do that, your brain will never adapt, you will never become geometric. You see? It's like the Nintendo DS, brain training. Okay? You have to do it and do it and do it again, and in the end, your brain is responding. This is the same thing. It's like brain training. Apply your brain to this, and you will see that as a benefit, you will start to understand better, you will start to think geometrically. So it's very formative, in my opinion. Okay. Thank you very much for your attention. I think we can stop here. Just if you could do me a favor, do it by yourself. This is the 3D extension of Cohen-Sutherland. Okay? As you can see, it's very easy once you understand the bidimensional method. So next time we will start from hidden surface removal. Thank you for your attention, and till the next.